Okay, what a great talk to follow on through. And it was great that he touched on a few of those identity implications with the Bitcoin system. So yeah, today I'm going to talk about digital signatures and identity in Bitcoin. And hopefully we can cover what are digital signatures, why use digital signatures, where are digital signatures used in the system, what is ECDSA, and how is identity implicated with the digital signatures in Bitcoin. So a digital signature is simply a unique numerical value that represents an assurance that a document hasn't been changed in time. So we can mutate an element that needs signing, and we can transform it into a value that will lie somewhere between 0 and 1.15 times 10 to the 77 or something like that. And these values, although they are a cryptographic artifact in that they can assist in proofs for data integrity and assurance and non-repudiation, which is the ability to, or the inability to deny that you were the one that made that that signature. They aren't a digital signature until, at law, until they are associated with identity. So Bitcoin uses the elliptic curve digital signature algorithm to reconcile transactions and add security to transactions that sit below a certain value level. But as soon as you're dealing with transactions that carry a value that meets certain specifications at law, you are required to have an identity element associated with that, whether it's an email address to get a receipt, or whether it's an address of where you're going to ship the good, or if you're transferring amounts over certain things. There are obligations from either party to retain some details for identity. So when they are done properly, though, we have that they are legal. So they're a legal equivalent to a wedding signature in most jurisdictions. They're algorithmic, so they become, as we can perform them on these computer systems and we get these numerical outputs, they can allow interoperability between other systems, as you can verify and recreate these signatures in the same fashion on a different device. So they're secure. Their security is well tested. They're defined by robust technical standards by bodies such as the NIST and other bodies that have been set up to manage digital signatures. And they allow the safe instant transactions that are at the heart of the Bitcoin protocol. And when I say they are at the heart of the Bitcoin protocol, I really mean that in the sense that an electronic coin is defined as a chain of digital signatures. It sounds a little bit confusing because we're thinking of these coins as specific units, but they themselves are simply an envelope, really. So you think of a Bitcoin and you think of a 1 Bitcoin, or I've got half a Bitcoin, but it doesn't really work like that because we have this UTXO model. A UTXO itself, which is, it defines a number of coins or a fixed number of the Satoshi tokens, and they are essentially locked in an envelope, and the lock is a predefined mathematical puzzle that will generally require the provision of a digital signature to solve that puzzle, and then we can open it up and spend those coins onwards. So you can see here that we've got the public key being input into the hash and the owner zero's digital signature, and we're chaining them all together. So they always can be traced back, their whole chain of provenance, back to when they were issued from the miners in that, or distributed onto the network by the miners. So we have these, this is a bit of a schematic for how the digital signature algorithm works, in that we have a message. You can set that there as the input message, and we put it through a hash function, and that's going to create a fixed length output depending upon the hash function, which will be deterministic based on the input, and it will be a one-way function, so it's impossible to figure out what that input message was from the message itself. And then we've got that hash digest, and we mutate it with the private key, and that produces a unique numerical value that's equivalent to a wedding signature, in that it's a unique combination of characters in a unique arrangement or style, as you would with a pen and paper. So you have a signed message then, and you provide that to the other party, and you can publicly disclose one of your keys to the other party, and they can verify that that signature was performed by another key that you keep private that has a mathematical relationship between the two. But that mathematical relationship is a one-way function. So it's easy to compute one way, but really difficult, pretty much impossible to reverse that process. And that property is the product of the elliptic curve discrete logarithm problem. So I think these slides got a little bit muddled up, but I'll just jump ahead one to the one-way function. It's achieved by leveraging the properties of modulo arithmetic. So modulo arithmetic is sometimes called clock arithmetic, as it's an arithmetic that really only deals sort of like with the remainder after a function has been performed. So 2 mod 10 is 2, 22 mod 10 is 2, 110 mod 2, 112 mod 2 is mod 10 is 2, and you're always just interested in that remainder. And so you can sort of think of it like a clock in the sense of if you've got the one slice of time and it shows 12 o'clock, the next slice of time shows 4 o'clock, it doesn't necessarily mean that 4 hours have passed. It could be 1 day and 4 hours, it could be 10 days and 4 hours. And so it's impossible to really know how many times around the clock you've been to yield that output. And similarly, it creates, so with ECDSA or elliptic curve digital signatures, we create a clock face with a huge number of hours, and that is a huge prime number. And with the elliptic curve itself, it's a really interesting property about the group of values that will lie on that elliptic curve, in that any operations upon them will yield another point on the curve. So we have this situation where it's like in a clock face, when you add 10 plus 3, it doesn't equal 13. Well, it does in 24-hour time, but it also equals 1. So we're just looping around on ourselves. So I'll go back one now. So this leads us into this, the process of elliptic curve point arithmetic. So it's a special kind of arithmetic where when you're operating on 2 points within that curve and you sort of fulfill the equations between the two, it'll yield another point on the curve. And so if we see up there, we've got points P and Q. When you draw a line that intercepts them, it intercepts the curve at a point which is the negative inverse of that, or the inverse of that addition process. So P plus Q intercepts the line at minus P plus Q. So because they are symmetrical about that x-axis, you can flip it back up and you then get that point. And if we then imagine that we've brought the Q back around on the underside to very close to it, or brought it back around the top side, those values are going to be converging. And so we can take a tangent for point doubling, and it's the equivalent of two values that are the same, and they will yield 2p on the curve. So when we need to mutate a private key by a very large number, we do multiple rounds of this point doubling to generate the big number, which is going to be your public key. And there is a method to enhance the efficiency of that, and that's this point doubling, where you take the binary representation of that string, that's ones and zeros, and you can actually just move those values along, and it becomes quite efficient. So you can do the multiplication of a 256-bit key in 256 operations, which a computer is able to do very quickly. So then once you have that key that you've created, or once you've got your key pairs, you can do something really interesting, which is this Diffie-Hellman key exchange. And that allows you to generate a shared secret between two parties across a public channel. So Alice is there and she has a private value, Bob has his private value, and they have a shared common public value. They both apply a process to the value, which will create their own separate discrete values themselves, and they can then pass that across a public channel and then change the value again. And through that process of sort of factorization, you end up with the same value that only you guys know. And you can use that value then to encrypt communications or to derive other key pairs along that, that both you, the parties, will know are going to be generated. And so then that allows us to create this sort of innovative privacy model and identity system, wherein in the Bitcoin privacy model, we have sort of everything's decoupled from one another, and the identity is then required to be managed by these second-order systems, dependent upon the specific use case. Whereas in the conventional privacy model, it should probably say trusted third parties, because we've got the credit card provider, your bank, the other party's bank, the payment network in there, and all those steps are just a vulnerability surface, that a potential that you can have a data breach or have your privacy exposed. So if we're generating a fresh key pair for each transaction, then we've created effectively this way that everything is decoupled from the identity, and you have to, as Jake said, you have to attack all these separate transactions rather than just attacking one central vault that's got all the goods in it. So this is some complicated stuff in here, but this is a white paper that's produced by nChain, which really documents the blockchain-based process of that elliptic, the Diffie-Hellman key exchange. And then through that, it's going to really, it has multiple applications. So we're going to be using it for secure authentication. We can use it for deriving key chains. We can use it for this interoperability because it's relying on these same technical standards. So if everyone's using the same derivation schemes, then we can really quickly sort of evaluate whether or not someone's got the value and whether it's going to be secure. And there are some implications for that in this IPv6 paradigm we're moving into, and we can start to transition into a peer-to-peer model where I can securely communicate with you and send stuff across that channel, and no one else is going to be able to, snoop on that channel, and it's just one, address in this vast address space that's going to allow us to, have an entirely new paradigm. So that's it. What have we got? Don't worry so much about that. That's a legacy one. But now I've got a demonstration of a tool that I've built, which I'm hoping can kind of demystify some of the process of signing a Bitcoin transaction. So I've made a new friend this year, Mr. GPT, and he's kind of advanced my capabilities far beyond they previously were. But I'm just waiting for this to come up on the screen here. Okay, cool. So this is connected to an isolated node that has a lot of the security parameters stripped out of it. It can generate a block instantly, and it can, it doesn't have to have the same consensus parameters of the normal network node. And through that, we can then just generate ourselves a few key pairs here. So you can see that we've got a private key, and that value is then mapped to this public key, and it also is then the Bitcoin address on this reg test network is created by doing hashing this value through SHA-256, and then hashing that again through the RIPE-MD 160. So we can choose now which key out of those ones we want to use to mine the blocks, and we'll just use the first one here. And this is going to give us, here we go, some spendable transaction outputs. And along the way here, I've got sort of these little info things that pop up that just give you a description of what's occurring there. But we can see in this, we've got a bunch of, details about this spendable transaction output. So it comes from a block number 960. That's the hash of the block, the TXID, the value that's contained in it, some of these script details. And we can now generate a transaction from scratch with this. So we're going to need a couple of these conversion tools because some of the values up here are expressed the wrong way around, essentially. So this TXID is provided in this response in big endian, but we need to change it around to little endian, so we can drop it in here and convert that. And we've now got a little endian value, and we can start to build out this transaction. So the version is just a field that's going to sort of specify which type of transaction we're handling here. And it's really important in this to be specific with the bytes that this data field is anticipating. So this is expecting a 4-byte hexadecimal value. So even though it's version 1, we have to write it in this particular format, which is the most important byte, or the little end of the byte is actually put at the other end And it's a little bit tedious, but it's, you start to get familiar with it. And then we're going to specify that this is just a one input, one output transaction. So here we require the TXID. So the V out, that's the index position of the output of the transaction that generated this. So we're spending Coinbase transactions. So they are the first transaction, the first output from that Coinbase reward. So it's going to have an index position of 0. The unlock script size. So at this point, because we haven't signed the transaction, we're going to be using the lock script as its placeholder one here. So this is actually provided in a decimal value as 25, but we'll just change that over to its hexadecimal representation, so we can put that in there. And then here's the unlock script. So the sequence number, that is specifying sort of what version of spending this input it is, and that's used in these payment channels. So we're not actually, you can't spend an input once it's been spent, but we can create these transactions that can be changed in some fashion through the incrementation of this sequence value. But because we want to have the transaction final straight away, this is like its finality state, we'll give it the maximum value that can be expressed in here, which is just all Fs. And we're going to use the sig hash flag, which will specify, what type of signature scheme we're going to use on this transaction. So we'll give it this 41, and there's some. You can expand out some info and find out what's going on here with these flags, because they're a little bit confusing, and we'll show a little bit more in shortly. And we're going to just generate one output itself. So here we need to specify the value that we're going to be spending. So up here we had 0.78 of a Bitcoin as this block reward, so we can change that over into a number of Satoshis, and then we can convert that to hexadecimal. And we've got 7 values there. So because we're expecting a 8-byte value here, we need to preface it with the leading number of zeros to pad out that 8 bytes. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Paste that in there. I haven't figured out how to remove these little spaces that go in when you're pasting it. And this is then the little endian representation of that value. But actually, because there is a transaction fee, I'll probably just take off, I'll change this to one layer lower, and we'll just convert that. And so there's a bit of copy pasting. It's quite a manual process, but hopefully that it, we're starting to see that this is what the machines are doing in the back end, creating these transactions. And here we'll just use that same lock script that we had before, because I'm just going to send the coins back to myself. So we'll, where is that? It needs optimization. Like, I'm not a web designer, so it's a bit clunky and everything, but it's still just allowing us to visualize that there. So the end lock time, that's going to specify at what block height or what Unix timestamp this transaction's able to be included into a block. So if I put 0, that's being interpreted as the block height, which is saying this transaction's able to be mined in any block that is after the first block of the blockchain. And we can then process the transaction data, and we've got, this is essentially the raw data that we're sort of going to go and spend. But we need to commit this data into a specific data structure, which is called the sig hash pre-image. So that's the data arrangement that's going to be then hashed to create that input message from that elliptic curve digital signature algorithm, where we will then sign that input message with the private key that we've got from that key pair. So we have a little bit of help here if we were going to be doing any of the other type of sig hash flags, it gives you some information about which values in this form below are going to be entered in as 0-byte values. And that will give you then the flexibility to add inputs into a transaction after you've signed the transaction, or add outputs into a transaction after you've signed it. So otherwise, adding a transaction into something that's told you to sign all the inputs, adding another input after that will invalidate that signature, and it won't be able to be approved by the network. So this allows you to say, just put some placeholder zeros in there, and you can create these flexible arrangements like a blank check that you could give to your child to go and buy some textbooks for university. So you said, here's $200, we haven't given you the outputs yet, so go and spend that in your way. Or we can swap it the other way around and say, here's a fixed output, this family's in need, let's everyone from the community add inputs into this transaction, and we know that it's only going to go to that party and not someone else along the way. So this is the pre-image template. So each input for a transaction, because we'll have a SIG hash flag applied to that, which can say that each one will have a different SIG hash pre-image. So we're going to go through and we'll just put that version in there. So here we've the previous outs, that's just going to require the transaction ID and its index position of every input that we're spending. So normally you would chain them all together through here, and then you hash that, which just commits it all to a single 32-byte value. So even if you've got 100 inputs, it still just reduces it to the 32 bytes. But if you weren't signing any inputs, you would just have the 0 bytes in through here. And then we're just doing one, so we've got the sequence number there, but when we're hashing that, we're also committing the finality of each of those transactions. So the out point is where we're going to send it. So we want to send it to the locking scripts ourselves. Oh wait, sorry, we've got they're both the same. The out point info, so it's the 36-byte out point of the input being used. Oh, sorry, this is because we're using a specific single transaction. Normally in this prev-outs thing, we'd have multiple ones chained if we had multiple inputs. But because we're just doing a single one, we're going to have just the transaction ID and its index position again. What's that? 1, 2, 3, 4, 5, 6, 7. The script code, which is then the size plus the locking script itself. Here, go there. The value. So this is not the value of what's being spent. It's the value of the transaction, the input that was committed to this transaction. So we need to go back here and get it, and we'll do that conversion again. Convert. Oh, sorry. We're getting this value back in here. So it's it's not a computer system would automate this, and there is lots of room for error. But I've designed this to hopefully be able to give students the ability to create these custom transactions and modify their lock scripts and unlock scripts, and sort of do some training exercises and such, and hopefully then we can become more competent and people can have this process kind of demystified. So the outputs is the transaction output value that we're going to get, so we can use that value which was here. So that's different. So the difference between these two values is, of course, being returned to the miner as the fees for the net that they're going to collect for their services of processing it. So where was I in this situation here? 19. All right. And we hash that data. So if there was multiple outputs in this transaction, they would have multiple ones through here. The unlock time is final, and the hash type is that SIG hash flag, but in this case it's entered in as a 4-byte little endian value. So it's not just the 41, it's going to have those zeros. And we're generating the pre-image here. So this string of characters is the input message, which is then going to be hashed and then signed in there. So we can hash the pre-images, and we've reduced that down to a 32-byte value. And now we can grab the private key from up here, from the input that we used, and sorry, I should have collapsed all these values because it gets a bit scrolly. Drop him in here, and we've got that SIG hash flag. So that's going to allow the miner, because we've appended the SIG hash flag here as well after we've hashed it, it'll tell them which way to recreate that pre-image so that they can validate that the message is the same that they're going to check the signature on. And we can sign the SIG hash. So now we have produced that digital signature. So that's here, this is that unique numerical value within a 256-bit space that, it's impossible for anyone else to create unless they've got that private key. And we can drop it into this space here. We'll grab the public key up here, which was in this field. And then, where am I? Here. And then we can generate the unlocking script. And this is the script that's going to solve that predefined puzzle. And I'll remember that value. And in here, I've tried to make it color-coded in some bits so we can, when we generate that raw transaction data, this is what you will see when you go to what's on chain or something and request the raw transaction data. So in here is that completed signature, and we can generate its transaction ID, and we can broadcast that transaction. Failed to send transaction. So, as I said, there's a lot of room for manual error, and it gets a little bit tedious here. Perhaps we can find out what its error message was. It hasn't given me, the key pool. No, it didn't give me the error message. So normally what happens here, I don't have time to go recorrect the process, but what happens is that we can just then provide that transaction ID, and we'll see, it will say, confirmed in a block with 0 confirmations. And as we go back up and we mine that 110 blocks over the top of it, we see the confirmation count increase, and we've successfully broadcast a transaction to that reg test network. But the only values that are really changed on on the real main network is that the address will have a little different prefix value here of a 1. The private key will have a different input format where the WIF format here specifies which network it's occurring on. So there's like one different value here, but the whole process is the same. But you are going to require, there'll be different ways of evaluating that signature and generating that lock script. So this is a pay to public key hash, but multi-sig will involve multiple signatures being input into this. You can pay to script hash, or there's lots of different transaction templates. So it's up to you guys when you're designing your systems to implement that sort of logic. But hopefully that sort of demystified the process a little bit, and you can see what there's not much data out there on that sig hash pre-image. So if you see that, okay, it's a rigid structure, but it allows for that flexibility with those 0-byte value fields that can, create this sort of rich potential for Bitcoin scripting and Bitcoin transaction templates to service any kind of conceivable transaction that we need to perform on, in commerce. So that's me for today. Sorry that it didn't give us the complete success, but we got to see how that whole process occurs. And that tool's available, or the GitHub repo, my one has that tool in there. But I'm going to, in the next month or so, it'll hopefully be hosted live as a resource for the Bitcoin SV Academy. And we've got a Bitcoin script course coming out soon that we can people can use that and tinker around with these tools and, understand this system a little bit more under the hood. So thanks a lot, guys, and enjoy your next presentation. Thank you.